The James Webb Space Telescope has just seen something that should not exist. A galaxy so massive, so bright, so fully formed, that by the rules of cosmic time it had no right to be there. We are looking back more than 13 billion years so close to the beginning that the universe was barely out of infancy, and instead of faint. Newborn flickers. We find a city of stars already blazing. It's as if we opened a history book to page 1 and found skyscrapers rising over a finished civilization, and now we have to ask what else grew up before the universe was ready. To understand how violent this discovery feels, we have to shrink ourselves. Imagine the entire 13.8 billion year history of the universe compressed into a single calendar year. The Big Bang happens at midnight on January 1st. The Milky Way forms in early spring. Earth appears in September. Dinosaurs roar in December. Humans arrive in the final minutes before midnight on New Year's Eve. This galaxy, it shows up in mid-January. Not as a scattered cloud, not as a faint shimmer of tentative light, but as something structured, heavy, mature, filled with stars that had already lived, burned, and enriched their surroundings with heavier elements. That means time had already passed inside it. Generations had already come and gone. And the universe was only a few 100 million years old. We are not supposed to see that. The early universe was simple: hydrogen, helium, darkness, gravity pulling gently on small ripples left behind by the Big Bang. For hundreds of millions of years, everything was quiet. No stars, no galaxies, just expanding gas cooling in the dark. Then gravity began gathering that gas into the first sparks of starlight, tiny proto-galaxies, fragile structures, the first stellar furnaces igniting. That's the story we expected. Instead, James Webb has found a galaxy that appears to have assembled the mass of billions of suns in a cosmic blink, a structure so substantial that, according to standard models, there simply wasn't enough time to build it. Picture trying to grow a redwood tree in a week. The laws of physics haven't changed. Gravity still pulls at the same strength. Matter still moves at the same speeds. The speed of light still caps how quickly information and structure can travel, and yet somehow, this galaxy compressed what should take 1 billion years into a few 100 million. We are staring at accelerated cosmic architecture. Webb didn't stumble onto this by accident. It was built precisely for this moment, unlike Hubble, which saw mostly visible and ultraviolet light. Webb peers into the infrared, and because the universe is expanding, ancient light stretches its wavelengths, pulled longer and redder as space itself grows. The farther we look, the redder the light becomes. Webb is tuned to that stretched light. So when it looked into the deep field, into a patch of sky so small it could hide behind a grain of sand held at arm's length, it wasn't just looking far away, it was looking back in time. Back to when the universe was less than 5% of its current age. And there it was, a galaxy glowing with unexpected intensity. At first, astronomers assumed it must be a trick of distance. Maybe it was closer than it appeared. Maybe its light had been distorted by gravitational lensing magnified by a massive object in front of it. Like a cosmic funhouse mirror, that happens. Space bends light. Massive galaxy clusters can amplify distant objects. But the spectral fingerprints didn't lie. Webb splits light into its component colours and reads it like a barcode. Every element leaves a pattern. Hydrogen, oxygen, carbon all carve distinct signatures into the light. And those signatures place the galaxy exactly where it shouldn't be deep in the early universe. Worse or better, it wasn't alone. Webb has found several galaxies from this era that appear too large, too luminous, too chemically evolved, each one like a skyscraper rising in what should have been an empty prairie. If these measurements hold, something fundamental about early galaxy formation is faster than we believed. Now we feel the scale of the problem. After the Big Bang, the universe expanded rapidly, then continued expanding more gently. Tiny quantum fluctuations, microscopic variations in density were stretched across cosmic scales. These slight overdensities became the seeds of galaxies. Gravity pulled matter into those regions. Dark matter, an invisible substance outweighing normal matter 5-to-1, formed massive halos first. Regular matter fell into those halos. Gas cooled. Stars ignited. But cooling takes time. Stars take time to form. Supernovae take time to enrich gas with heavier elements, allowing the next generation of stars to form more efficiently. You cannot rush fusion. Or can you? Because this galaxy seems to have done exactly that. It suggests that either star formation in the early universe was extraordinarily efficient, far more aggressive than our models predict, or that dark matter clumped more quickly, or that the conditions immediately after the Big Bang were not as smooth as we thought. And here's where it becomes personal. Every atom in your body, every carbon atom in your cells, every oxygen molecule you breathe was forged in stars. Not the first stars, but later generations, enriched by earlier explosions. If galaxies formed faster, if stars ignited earlier, then the ingredients for life began circulating sooner than we imagined. We are looking at a galaxy that may have accelerated the cosmic timeline itself. Imagine standing on a young Earth and looking up at a night sky already thick with ancient starlight long before Earth even existed. That is what Webb is revealing. Not just an early galaxy, but a universe that may have wasted no time becoming complex. The early cosmos might not have been a slow dawn, it may have been a flash flood. And if that's true, then our origin story, the slow, patient assembly of structure, needs revision. Not because physics failed, but because it might be more efficient, more ruthless, more ambitious than we thought. This galaxy is not breaking the laws of nature. It is revealing how powerful those laws truly are. Gravity does not hesitate. Given even slight irregularities, it amplifies them relentlessly. A slightly denser region becomes a magnet. Gas streams in. Pressure rises. Stars ignite. Radiation pushes back. Shock waves ripple outward. And if the density is high enough, the process snowballs. What if the early universe had more of these seeds than we estimated? What if the cosmic web, the vast filaments of matter stretching across billions of light years, condense faster in certain regions, forming gravitational highways that funnel material into newborn galaxies? Then growth could happen in surges. And this galaxy would not be an anomaly. It would be a clue, a glimpse into an era where the universe was young, dense, and extraordinarily fertile. Because back then, everything was closer together. Space had not yet stretched as wide. Matter was packed tighter. Interactions were more frequent. Collisions more common. Gas reservoirs more abundant. It was a crowded cosmic nursery. And in crowded nurseries, some children grow fast. In that crowded nursery, gravity did not whisper. It roared. When the universe was only a few 100 million years old, its average density was dozens of times higher than it is today. Galaxies were not isolated islands drifting in vast emptiness. They were forming inside a tighter, hotter, more chaotic environment where streams of gas flowed along invisible filaments of dark matter like rivers feeding a delta. If you could hover above the early cosmos, you wouldn't see scattered sparks. You would see a web, colossal strands of matter stretching across space, intersecting at dense nodes. At those intersections, gravity tightened its grip. Gas didn't gently drift inward, it poured. Now imagine standing inside one of those intersections. Hydrogen clouds collapsing at thousands of kilometers per second, temperatures rising, pressure mounting, and then ignition. The first stars in that region flaring to life, massive, blazing, short-lived. The earlier stars were not like our sun. Many were likely dozens or even hundreds of times more massive. They burned hotter, brighter, and faster. Some may have lived only a few million years before detonating as supernovae violent enough to outshine entire galaxies for brief moments. That means enrichment could happen quickly. When those first titanic stars exploded, they seeded their surroundings with heavier elements: carbon, oxygen, nitrogen, Silicon, the raw ingredients for future generations of stars, for planets, for chemistry. In our previous picture of the early universe, this cycle collapse, ignition, explosion, enrichment. Repetition was expected to take time, hundreds of millions of years before galaxies gained substantial mass, before they shone with sustained brightness. But what Webb has seen suggests that cycle may have run at breakneck speed. The galaxy it detected appears to contain billions of solar masses worth of stars, not a scattered handful, not a faint shimmer, a structured, luminous system already well on its way to maturity. To feel how extreme that is, shrink the Milky Way down. Our galaxy contains roughly 100 to 400 billion stars and spans about 100,000 light-years across. It took billions of years to assemble that structure. Mergers, accretion, gradual growth. Now imagine compressing that developmental arc into a fraction of that time. The galaxy Webb found may not rival the Milky Way in size yet, but for its age, it is enormous, like discovering a fully grown adult in a nursery of infants. And here is the unsettling part. The brightness we see implies intense star formation. Stars are factories of light. The more massive and numerous they are, the more a galaxy shines. If this galaxy is that luminous, it means it was forming stars at a furious rate, possibly dozens or even hundreds of solar masses per year. For comparison, the Milky Way today forms about 1 to 2 solar masses of stars per year. This early galaxy may have been building stars 100 times faster. That is not gentle growth. That is cosmic acceleration. We begin to feel the pressure this puts on our models, because cosmology is not guesswork. It is built on precise measurements, cosmic microwave background radiation, large-scale structure surveys, simulations run on supercomputers modelling billions of particles of dark matter evolving over billions of years. Those simulations start with the known physics of the early universe. They let gravity operate. They allow gas to cool. They include feedback from supernovae and radiation. And they predict a timeline. If multiple galaxies appear too massive, too bright, too chemically evolved at these early times, then one of 3 things must be true. Either we are misinterpreting what we see, or our measurements of mass and age need refinement, or the early universe was more efficient at building structure than our simulations allow. None of those options are trivial. But none of them mean the universe is broken. They mean we're still tuning our understanding of how quickly gravity can sculpt matter when conditions are extreme. There is something else happening in that early epoch, something even more profound. The universe was undergoing what astronomers call reionization. After the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen. That neutral gas filled space and absorbed light. It was opaque in certain wavelengths, a fog. Then the first stars and galaxies began emitting intense ultraviolet radiation. That radiation tore electrons away from hydrogen atoms, again ionizing the gas and making the universe transparent to certain forms of light. This was not a quiet process. It was a phase transition on a cosmic scale. Bubbles of ionized gas expanding outward from young galaxies, merging, overlapping, transforming the universe from murky to clear. If galaxies like the one Webb found were more common or more powerful than expected, they may have driven reionization faster than we believed. They would not just be passive residents of the early universe. They would be architects of its transformation. Imagine being inside one of those early galaxies. You are surrounded by brilliant short-lived stars blasting ultraviolet radiation into space. Supernova shockwaves ripple through dense clouds. Black holes at galactic centers may already be forming, feeding on infalling matter, releasing jets of energy that pierce the surrounding gas. It is not a calm environment. It is a furnace. And yet, in that furnace, structure stabilizes, gravity counters explosion, gas collapses again, new stars form from enriched material. This is the paradox chaos builds order. We are witnessing a universe that did not crawl toward complexity. It surged. And that surge carries implications for us. Because if galaxies matured earlier, then black holes may have grown earlier. If black holes grew earlier, then gravitational interactions, energetic feedback, and heavy element distribution all began sooner. The timeline compresses. The universe may have reached chemical richness faster. And chemical richness is the prerequisite for planets, for atmospheres, for oceans, for biology. We are not saying life existed 13 billion years ago. We are saying the stage may have been set sooner than expected. You can feel the shift. Instead of a slow unfolding, the cosmos becomes urgent. Instead of a patient assembly line, it becomes a pressure cooker. And we are only beginning to see this because James Webb is doing what it was designed to do, catch the faintest, reddest whispers of ancient light. But these whispers are not faint anymore. They are loud enough to challenge our assumptions. And this is only the beginning. Because if one galaxy appears too mature and then another and another, a pattern emerges. And patterns in the cosmos are never small. Patterns in the cosmos are never small. They are tectonic. When multiple galaxies appear earlier and heavier than expected, we are not looking at statistical noise. We are looking at pressure building beneath the surface of our understanding. One outlier can be dismissed. A handful becomes a signal. And Webb's deep fields are starting to look less like isolated surprises and more like a crowded skyline. To grasp what that means, we have to confront the invisible foundation beneath every galaxy: dark matter. You cannot see dark matter. It emits no light. It absorbs none. It does not glow, flicker, or flare. But its gravity dominates the universe. For every kilogram of ordinary matter, the atoms that make up stars, planets, and you, there are roughly 5 kilograms of dark matter shaping the large-scale structure of space. Galaxies form inside halos of this invisible substance. Think of dark matter as scaffolding. Ordinary gas flows into its gravitational wells. Without it, galaxies would not hold together. Without it, stars would drift apart. So if galaxies formed faster than expected, perhaps the scaffolding assembled faster. In the earliest moments after the Big Bang, tiny quantum fluctuations were stretched across cosmic scales during inflation. These fluctuations became slight differences in density regions that were just a little bit heavier than their surroundings. Gravity amplified those differences relentlessly. The denser regions pulled in more matter, becoming denser still. Over time, this runaway process built the cosmic web filaments and nodes of dark matter spanning billions of light years. Simulations of this process are astonishingly detailed. Supercomputers evolve virtual universes forward in time, particle by particle, obeying known physics. They produce a universe that resembles what we observe today: clusters of galaxies connected by filaments, vast voids in between. But those simulations rely on assumptions about how quickly small structures merge into larger ones. If Webb is seeing mature galaxies at redshifts corresponding to only 300 or 400 million years after the Big Bang, then either the dark matter halos were denser earlier, or gas cooled and collapsed into stars more efficiently, or mergers happened faster and more violently, or some combination of all three. None of those options require new laws of physics. But they do require recalibration. And recalibration at this scale is not cosmetic. It reshapes our narrative of cosmic childhood. Let's step inside one of these early halos. A region of space slightly denser than average begins to collapse under its own gravity. Dark matter, which interacts primarily through gravity, forms a growing clump. Ordinary gas, mostly hydrogen and helium, falls inward along filamentary streams. As it falls, it heats up. Collisions between particles convert gravitational energy into thermal energy. But if the gas can radiate that heat away through atomic transitions, through emission lines it cools. Cooling allows it to collapse further. The first stars ignite. These early stars likely lacked heavy elements, which means their cooling processes were different. They may have grown larger because metal pour gas fragments less efficiently. Larger stars burn hotter and die sooner. Short lifetimes mean rapid supernovae. Supernovae mean shock waves compressing nearby gas. Compressed gas forms new stars. The cycle accelerates. Now imagine multiple streams of gas feeding the same halo simultaneously. Instead of one gentle inflow, you have several rivers converging. Each carries fresh fuel. Each deepens the gravitational well. The galaxy's central region becomes a crucible. Stars form not in scattered pockets, but in dense clusters. Their radiation carves cavities in surrounding gas. Supernovae inject turbulence, yet the overall gravitational pull remains dominant, pulling material inward faster than feedback can expel it. This balance between inflow and feedback determines growth. In the present-day universe, feedback often regulates star formation. Too many massive stars form, and their radiation and supernova push gas away, slowing further growth. But in the early universe, gas densities were higher, inflows were stronger. It may have been harder for feedback to shut down star formation completely. Growth could outpace regulation. That is how you build something massive quickly. And Webb's measurements suggest precisely that intense star formation rates, high stellar masses, and in some cases, indications of surprisingly evolved chemical compositions. If heavy elements are already present, that implies previous generations of stars had time to live and die, which means star formation started even earlier than we are directly observing. We are seeing the result, not the beginning. It is like finding an old forest and realizing the first saplings sprouted long before the earliest trees you can see. This pushes the onset of galaxy formation closer to the Big Bang itself, closer to the era when the cosmic microwave background, the faint afterglow of the Big Bang, was still dominating the radiation field of the universe. That radiation was not gentle. It permeated space. It influenced how gas cooled and collapsed. And yet, somehow, structure punched through. Now place yourself in that timeline. The universe is only a few 100 million years old. No planets yet. No stable, metal-rich solar systems like ours. No biology. But already, galaxies are blazing. Already, black holes may be forming in their centers. Some of the earliest supermassive black holes we have detected appear less than 1 billion years after the Big Bang, weighing millions or even billions of times the mass of the Sun. Growing a black hole that large so quickly is another puzzle. Black holes grow by accreting matter, but there are limits to how fast they can consume material without radiation pressure pushing it away. That limit, the Eddington limit, sets a theoretical cap on steady growth. And yet, we see black holes that appear to have approached enormous masses very early. If galaxies grew fast, perhaps their central black holes did too. Perhaps dense inflows fed them aggressively. Perhaps early conditions allowed near-continuous accretion. Every accelerated galaxy strengthens the case for accelerated black holes. And accelerated black holes change everything. Because supermassive black holes are not passive objects. When actively feeding, they release enormous amounts of energy, sometimes outshining their host galaxies. Jets of relativistic particles blast outward, radiation heat surrounding gas. They regulate galaxy evolution. So now we are looking at a picture where not only did galaxies assemble quickly, but their central engines may have ignited early as well. This is no longer a quiet dawn. It is an era of extreme growth, extreme radiation, extreme transformation. And we are just now peeling back the curtain. Webb is not just finding isolated curiosities, it is mapping an epoch that was far more dynamic than our previous telescopes could reveal. The early universe is beginning to look less like a fragile beginning and more like a proving ground. A place where gravity tested its strength under the most favourable conditions it would ever have. Dense matter, abundant fuel, minimal dilution, everything close together. If structure could grow explosively anywhere, it would be there. And now, staring at these galaxies, we feel something shift inside our understanding. The universe did not hesitate. It did not wait to become grand. It rushed. It rushed. Before the universe had even celebrated its first billionth birthday, it was already building metropolises of stars. And that speed changes how we imagine the first light ever switching on. For decades, astronomers spoke of the cosmic dark ages as though they were long and quiet. After the Big Bang's initial blaze faded, the universe cooled into darkness. No stars, no galaxies, just neutral hydrogen stretching in all directions, absorbing light and filling space like a dim fog. Then gravity began its patient work. That was the assumption patient. But Webb's discovery suggests the Dark Ages may have ended not with a whisper, but with an eruption. Picture it. For perhaps 100 to 200 million years, the universe is dark, matter is clumping invisibly, the seeds are there, but nothing shines yet. Then, in pockets across the cosmos, the first massive stars ignite. They burn blue-white and ferocious. They live fast and die violently. Each explosion sends shockwaves across surrounding gas. Instead of a slow sunrise, it may have been a chain reaction. Light begetting more light. Each early galaxy becoming a beacon in a once-black universe. The galaxy Webb detected is not merely bright for its time. Its very existence implies that the processes behind it were already well underway. To assemble billions of solar masses in stars, gas had to collapse efficiently. Star formation had to proceed in bursts. Feedback had to be strong enough to shape structure, but not strong enough to shut it down. This is a narrow balance, and the early universe appears to have found it quickly. There is something almost unsettling about that. Because when we imagine beginnings, we imagine fragility, we imagine trial and error, slow experimentation. Instead, the cosmos may have entered adolescence almost immediately. Let's anchor ourselves again. Today, if you look up at the night sky from a dark location, you might see a few thousand stars with the naked eye. If you use a small telescope, you might see distant galaxies as faint smudges. With powerful observatories, we see billions of galaxies scattered across the observable universe. Each one took billions of years to grow into its present form. But Webb is showing us that some galaxies were already substantial when the universe was only 3% of its current age. That compresses the timeline dramatically. To feel that compression, imagine building a city the size of New York in a single afternoon. Foundations poured, skyscrapers raised, electrical grids wired, subways dug, people moving in. That is the kind of acceleration we are confronting. Now consider the physics that must cooperate for that to happen. Gas must cool rapidly. Cooling requires mechanisms. In a metal-poor universe, hydrogen and helium dominate. They are not as efficient at radiating away heat as heavier elements, yet somehow, cooling proceeded well enough to allow fragmentation and star formation at scale. Perhaps the first stars enriched their surroundings faster than expected. Perhaps turbulent flows enhanced cooling. Perhaps dense regions shielded themselves from background radiation more effectively. Every possibility points in the same direction: early efficiency. And then there is the role of mergers. Galaxies grow not only by forming stars, but by colliding and merging with other galaxies. In the early universe, distances were smaller, structures were closer together, collisions were more frequent. Two small proto-galaxies merging can trigger starburst intense periods of star formation driven by compressed gas. Now imagine a sequence of rapid mergers in a dense node of the cosmic web. Small halos combining into larger ones, gas funneled inward, star formation ignited in waves. Instead of gradual accumulation, you get stepwise leaps in mass. That could explain how a galaxy appears to jump ahead of schedule. And if this happened in multiple regions, it suggests that the early universe was more interconnected than we imagine, more dynamic, more prone to runaway growth in certain hotspots. There is another layer to this. When we observe these distant galaxies, we are not seeing them as they are now. We are seeing ancient photons, packets of light that have been travelling for over 13 billion years, stretched by cosmic expansion along the way. Those photons left their galaxy when Earth did not exist, when the Sun had not formed, when our Milky Way was itself a young and evolving structure. They have crossed expanding space for nearly the entire history of the cosmos, and now they are caught by a golden mirror orbiting 1,000,000 miles from Earth. That alone should feel impossible. But what those photons reveal is even more destabilizing. They reveal that complexity emerged early. That structure did not wait for comfort. That gravity, given the right conditions, wastes no time. We are forced to reconsider the temperament of the universe. Was it cautious? Or was it aggressive? Webb's observations lean toward aggression, toward a cosmos eager to collapse, ignite, and organize itself. And yet, nothing about this violates known physics. Gravity has always been relentless. Density amplifies density. Once collapse begins, it accelerates. Once stars ignite, they transform their surroundings. Once black holes begin feeding, they influence entire galaxies. Perhaps what we are witnessing is not an anomaly, but the natural consequence of a universe that began hot, dense, and primed for structure. In that environment, hesitation is rare. Now bring it back to us. Every heavy element in your blood, every calcium atom in your bones, traces its lineage back to ancient stars, if galaxies matured earlier. Then the enrichment of the universe began earlier. The raw materials for rocky planets and complex chemistry started circulating sooner. That does not mean life emerged instantly, but it means the cosmic clock toward habitability may have started ticking earlier than we assumed. Somewhere in that early blaze, the first generations of stars lived and died, forging the periodic table beyond hydrogen and helium. And now, billions of years later, we look back and see their aftermath. We are not just observing distant light. We are observing ancestry. The galaxy that should not exist is not breaking the universe. It is revealing how quickly the universe learned to build. And as Webb continues to stare deeper, longer, and with sharper infrared vision than any telescope before it, we may find that this early maturity is not rare. If so, the early cosmos was not a blank canvas slowly painted over time. It was a furnace, roaring to life almost immediately. And we're only beginning to feel its heat. And the deeper we look, the more that furnace refuses to cool. Because once you accept that one galaxy formed too fast, you begin to ask the more dangerous question. How many did? Webb's surveys are not random snapshots. They are systematic excavations of cosmic time. Astronomers point the telescope at a tiny, seemingly empty patch of sky and let it stare. Hours turned into days of exposure. Faint photons accumulate. The darkness fills with structure. What once looked like nothing becomes crowded. And in those crowded frames, more candidates appear galaxies whose light has been stretched so severely by expansion that it arrives deep in the infrared. Their redshift values place them astonishingly early, some less than 400 million years after the Big Bang, some possibly earlier. Each detection tightens the pattern. At first, researchers were cautious. Maybe brightness was being overestimated. Maybe dust properties were skewing measurements. Maybe stellar populations were being misread. But spectroscopy, the splitting of light into its detailed components, adds weight. It provides chemical fingerprints and distance confirmations, and in several cases, those confirmations hold. These galaxies are not illusions. They are early, very early. Now feel the tension this creates inside cosmology. The standard model of cosmology, Lambda CDM, is one of the most successful scientific frameworks ever built. It explains the cosmic microwave background with exquisite precision. It predicts the distribution of galaxies across billions of light years. It accounts for dark energy accelerating expansion. It works. But models are tuned to data, and Webb has just delivered data from a regime we have never seen clearly before. If galaxies this massive are common at such early times, simulations may need to adjust assumptions about star formation efficiency, feedback strength, or dark matter clustering on small scales. This is not a collapse of theory. It is refinement under pressure. But refinement at the beginning of the universe echoes forward across all cosmic history. Because early structure sets the stage for everything that follows. Let's step back into that early era again. The universe is small compared to today. Not spatially small in the sense of a contained sphere, but dense. If you could take a cubic region of space from that epoch and bring it into today's universe, it would contain far more matter packed into the same volume. More matter means stronger local gravity. Stronger gravity means faster collapse. Faster collapse means earlier ignition. It is possible that our intuitions were simply too conservative, that we underestimated how violently structure can emerge when the density dial is turned up. Think of rainfall. A light drizzle gathers slowly, puddles form gently. But in a monsoon, water overwhelms the ground in minutes. Rivers swell, floodplains disappear. The early universe may have been a gravitational monsoon. Dark matter halos forming rapidly, gas streaming inward in thick currents, star clusters igniting in bursts so intense they reshape their environment before fading. And in the centre of some of these galaxies, something even more extreme may have been forming. Black holes. Not the stellar mass black holes left behind by dying stars, but seeds of supermassive black holes, objects millions or billions of times more massive than the Sun. The existence of supermassive black holes less than 1 billion years after the Big Bang has long been a puzzle. Growing one requires either starting with an unusually massive seed, or sustaining near-continuous accretion at extreme rates. If galaxies were assembling faster and feeding central regions with dense gas flows, that growth becomes more plausible. Dense early galaxies could have created perfect feeding grounds. And once a black hole reaches a certain mass, its influence expands dramatically. Accretion disks blaze with radiation. Jets punch through interstellar gas at near-light speeds. Entire regions of galaxies are heated or expelled. This is feedback on a colossal scale. So now imagine an early universe where galaxies are growing quickly and central black holes are igniting early. You have not just a furnace. You have an engine room. Light pouring outward, radiation carving bubbles in hydrogen fog, ionized regions expanding and merging. This ties directly into reionization, the transformation of the universe from neutral to ionized. The speed and intensity of early galaxy formation determine how quickly that fog lifts. If Webb's galaxies are as powerful as they appear, they may have contributed significantly to clearing the early cosmos. That means these unexpected galaxies are not just anomalies. They are participants in one of the greatest phase transitions in cosmic history. Now pause and feel what that means. We are watching the universe wake up. Not gradually, but decisively. The photons reaching Webb today began their journey when the cosmos was still transitioning from darkness to transparency. They have travelled across expanding space for over 13 billion years, dodging nothing, encountering almost nothing, because space is mostly empty. And now they land on a mirror the size of a tennis court orbiting far beyond the moon. That mirror focuses them into instruments cooled near absolute zero. Detectors measure them with astonishing sensitivity. And from those faint signals, we reconstruct the architecture of the early universe. There is something almost poetic about that. Ancient light meeting modern technology. The infancy of the cosmos intersecting with the maturity of human curiosity. But curiosity alone is not what drives this. It is scale. When a galaxy forms too early, it challenges not just equations, but intuition. We like orderly timelines. First simplicity, then gradual complexity, then sophistication. Instead, the cosmos may have leaped. And leaps are unsettling. Because they imply that under extreme conditions, growth is not linear, it is exponential. A slight advantage in density becomes overwhelming dominance. A a slightly earlier ignition becomes cascading structure. The early universe was a place where small differences amplified rapidly. And if that is true, then perhaps our models of early galaxy suppression where feedback was expected to slow growth were too cautious. Perhaps feedback and inflow danced in a tighter balance than expected. Perhaps the early cosmos tolerated extremes. The key is this: nothing we are seeing requires magic. It requires intensity. And the early universe had intensity in abundance. The question is no longer whether one galaxy grew too fast. The question is whether we have underestimated how aggressive gravity can be when everything is closer together, hotter, denser, and primed for collapse. Because if gravity had its most powerful era at the beginning, then what Webb is revealing is not a violation. It is gravity at its peak. Gravity at its peak is not subtle. It does not negotiate. It does not hesitate. It takes the slightest unevenness in the fabric of space and amplifies it until the difference becomes destiny. In the early universe, those unevennesses were everywhere. After cosmic inflation stretched microscopic quantum fluctuations across unimaginable scales, the universe was left almost but not perfectly smooth. Density variations were tiny. 1 part in 100,000. That's all it took. That fractional imbalance became the blueprint for everything. In today's universe, gravity works against expansion across enormous distances. Galaxies are separated by millions of light years. Dark energy accelerates that separation. Matter is diluted. But rewind to 300 million years after the Big Bang, and the rules feel sharper. The universe was smaller by a factor of several. Matter was compressed. The cosmic web's filaments were thick with potential. Under those conditions, gravity didn't need billions of years to experiment. It could act decisively. Now imagine a region slightly denser than average. Dark matter begins to clump, forming a halo tens of thousands of light years across. Gas streams inward along filaments like fuel lines feeding a reactor. As it falls, it heats. As it cools, it collapses further. Then ignition. Not one star, but clusters dense knots of stellar birth. Massive stars dominating the light output. Radiation floods outward, ionizing nearby gas. Supernovae explode, compressing neighboring clouds. But here's the crucial difference in such dense environments. Expelled gas doesn't travel far before gravity pulls it back. Feedback loops don't end growth. They recycle it. That recycling could be the hidden accelerator. Instead of shutting down star formation, early feedback may have stirred the gas, enriching it and driving turbulence that made further collapse easier. A kind of cosmic churn, violent but productive. And so a galaxy swells. Stars form in bursts. Gas flows continue feeding the center. Mergers with neighboring proto-galaxies add mass in sudden increments. Within a few 100 million years, what should have been a faint glimmer becomes a luminous structure visible across 13 billion years of space-time. When Webb captures its light, we are seeing the result of compounded acceleration, and it forces us to rethink the pace of early cosmic history. Because early galaxies are not isolated curiosities. They are boundary markers. They tell us how fast complexity can emerge from simplicity. Hydrogen and helium alone are chemically basic. They cannot form rocky planets. They cannot build complex molecules like DNA. They are raw ingredients without texture. Heavy elements, carbon, oxygen, nitrogen, iron are forged in stars and distributed through supernovae. If galaxies formed and evolved quickly, then heavy elements began circulating sooner. Which means the universe may have reached chemical diversity earlier than we thought. This does not imply early life, but it does shift the timing of possibility. Picture the timeline again. If the universe is a year long, and these galaxies appear in mid-January, then the forging of complex elements begins weeks earlier than expected on that calendar. By spring, the cosmos could already be seeded with the building blocks of planets. By summer, rocky worlds might begin forming around second or third generation stars. The universe may not have waited long to become interesting. And yet, we must hold something steady here. The standard cosmological model still describes the large-scale universe with astonishing accuracy. The cosmic microwave background remains one of the most precisely measured phenomena in science. The distribution of galaxies across billions of light-years matches predictions remarkably well. What Webb is probing is a frontier small scales, early times, extreme environments. It is like zooming into the first minutes of a volcanic eruption and realizing the magma flowed faster than expected. The mountain still exists, the eruption still follows physics, but the early dynamics are more intense than our initial models captured. And intensity changes narrative. Because when we look back at the early universe now, we no longer see a fragile baby cosmos cautiously lighting its first candles. We see a dense arena where gravity competed fiercely against radiation and expansion, and often won. We see a universe that may have entered its creative phase almost immediately. There is another layer here that deepens the tension. Observing these early galaxies depends on interpreting faint light that has travelled for billions of years. The further back we look, the more redshift stretches the wavelengths, the more cosmic expansion dims the brightness, the more intervening hydrogen absorbs certain frequencies. Webb is operating at the edge of detectability. That means every measurement carries uncertainties. Mass estimates depend on modelling stellar populations. Age estimates depend on interpreting spectral features. Dust can obscure light and complicate readings. So part of the scientific community is carefully reanalyzing these observations. Are we overestimating masses? Are we misclassifying young starbursts as mature systems? Could some of these galaxies be less massive but unusually bright due to intense, short-lived star formation? These are valid questions. But here is what makes the moment powerful. Even conservative revisions still leave us with galaxies forming earlier and more robustly than previously observed. The direction of the story remains the same. Earlier, faster, brighter. And if that pattern holds as more data arrives, it suggests something profound about the early cosmos. It suggests that once gravity had the right conditions, high density, abundant gas, minimal interference, it moved with extraordinary efficiency. The early universe may have been the most productive era of structure formation it would ever experience. Later, as expansion stretched space and dark energy began to dominate, growth slowed, galaxies became more isolated, star formation rates declined. Today, the universe is quieter. The cosmic star formation rate has dropped dramatically compared to its peak about 10 billion years ago. We live in a calmer epoch. But Webb is showing us the opposite extreme, the age of urgency. And there is something humbling about that, because it reminds us that our cosmic story is not centered on us. By the time Earth formed 4.5 billion years ago, the universe was already ancient. Generations of stars had lived and died. Galaxies had collided and reshaped themselves. Supermassive black holes had grown monstrous. We arrived late. Very late. Yet through instruments like Webb, we can look back and witness the universe's earliest surges. We can watch gravity at its most aggressive. We can see structure rising out of primordial chaos with astonishing speed. And that realization reshapes how we imagine beginnings. Not as fragile, but as fierce. Fierce beginnings change how we measure time. Because if the early universe was capable of building galaxies at breakneck speed, then the first billion years were not a gentle preface, they were a crucible. And crucibles do not produce delicate things. They produce extremes. Let's go deeper into that crucible. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Light was finally free to travel without constantly scattering. That ancient light still fills the cosmos today as the cosmic microwave background, a faint afterglow, stretched into microwaves by expansion. For millions of years after that, there were no stars, just expanding gas and invisible dark matter halos forming quietly in the dark. Then something tipped. When the first regions reached sufficient density, collapse accelerated, gas compressed, temperatures rose to millions of degrees in protostellar cores, nuclear fusion ignited. The first stars turned on. But here's what we are beginning to realize once that first ignition happened. It may have triggered a cascade. Massive early stars emitted enormous amounts of ultraviolet radiation. That radiation ionized surrounding hydrogen, creating expanding bubbles of charged plasma. At the same time, supernova explosions injected shock waves into nearby gas clouds. Those shock waves didn't just destroy. They compressed. Compressed gas collapses faster. Faster collapse forms more stars. More stars create more radiation and more supernovae. This is not a slow chain of events. It is amplification. And if this amplification happened inside dense dark matter halos fed by constant gas inflow, it could sustain astonishing rates of star formation. Which brings us back to the galaxy Webb has seen. Its brightness is not subtle. To shine across 13 billion years of expansion, its light had to be intense at the source. That implies either an enormous number of stars or a burst of star formation so powerful that it temporarily outshone its mass. Either way, it signals efficiency. And efficiency in the early universe is a dangerous idea in the best way. Because for decades, we assumed the early cosmos was limited by cooling times and feedback regulation. That early star formation would sputter and stall under its own radiation pressure. But what if, under higher densities and constant inflow, feedback was less effective at shutting things down? Imagine trying to extinguish a bonfire while someone continuously dumps more wood onto it. You can kick sparks, you can scatter embers, but the fire keeps growing. The early universe may have been that fire. Now zoom out. If multiple galaxies are forming rapidly across the cosmic web, then entire regions of space are lighting up almost simultaneously. Ionized bubbles expand outward from each galaxy. Over time, those bubbles intersect and merge. Eventually, the fog of neutral hydrogen clears. The universe becomes transparent to ultraviolet light. That transition reionization marks a profound shift in cosmic history. And galaxies like the one Webb detected may have played a starring role. We are not just seeing isolated growth. We are seeing agents of transformation. And there is another consequence. Earlier star formation means earlier supernovae. Earlier supernovae mean earlier enrichment. Earlier enrichment means that by the time the universe is 1 billion years old, many galaxies may already contain significant amounts of carbon, oxygen, silicon, iron. Those elements cool gas more efficiently than hydrogen alone. They allow gas clouds to fragment into smaller clumps. Smaller clumps form lower mass stars like our Sun, which live longer, which provide stable energy output for billions of years, which allow planets time to form and evolve. If enrichment started earlier, then the conditions for long-lived stars and planetary systems began earlier too. Again, this does not mean life sprang up instantly, but it means the cosmic runway toward habitability was extended further back in time. The universe may have become capable of supporting complexity earlier than we assumed. There is something quietly radical about that. Because when we think about our place in time, we often imagine ourselves emerging after a long, necessary build-up, as though the universe needed most of its 13.8 billion years to prepare for observers. But Webb's discoveries hint that the universe may have been chemically interesting far earlier. We may not be the product of a slow cosmic rehearsal. We may be the product of an early explosion of structure whose consequences unfolded over billions of years. And that changes the emotional texture of the story. It makes the universe feel less hesitant, more ambitious. Now bring it back to scale. The light Webb captures from these galaxies began its journey when the universe was smaller by a factor of roughly 10. Every wavelength has been stretched tenfold by expansion. Every photon has crossed a universe that grew dramatically during its transit. Those photons left their galaxy before the Milky Way had its current shape. before the sun formed, before Earth solidified, before the first cell divided, they have been travelling for nearly the entire history of everything we know, and they arrive with a message. We built early. We built fast. We built big. There is a kind of audacity in that. And yet, we must remain grounded. Astronomy is careful. Follow-up observations are underway. Spectroscopic confirmations are refining distances. Stellar mass estimates are being recalculated. Some early claims may soften under scrutiny. But even softened, the pattern is undeniable. The early universe was not empty for long. It did not linger in simplicity. Once gravity found its footing, it surged. And we are witnessing that surge in real time, not because it is happening now, but because its light has finally reached us. James Webb was designed for this moment. Its segmented mirror unfolds like a mechanical flower. Its instruments operate in the cold shadow of a 5-layer sunshield, shielding it from the warmth of the sun and earth. It orbits a gravitational balance point 1,000,000 miles away, where it can stare into deep time without interference. All of that engineering, decades of design, billions of dollars, thousands of scientists was built to answer one question. What did the universe look like at the beginning? And the answer emerging is not quiet. It is not timid. It is explosive. The early cosmos was a place where gravity reached towards structure with urgency, where light ignited in bursts, where galaxies rose sooner than expected, and we, billions of years later, are finally catching up to that blaze. Catching up to that blaze changes us, because for the first time in history, we are not guessing at the universe's childhood from distant echoes. We are seeing it directly through stretched, ancient light that has crossed almost the entire age of existence. And what we're seeing does not behave like a hesitant beginning. It behaves like momentum. Momentum is the key. The early universe was not starting from zero complexity. It was starting from extreme density, extreme temperature, extreme energy. Even after expansion cooled it enough for atoms to form, the baseline conditions were still far more intense than anything we experience today. Gravity had more to work with. And when gravity has more to work with, it compounds faster. Picture 2 scenarios. In the first, you sprinkle a handful of sand onto a table and try to form a pile. It takes time. You gather grains slowly. In the second, you dump a truckload of sand in one spot. A mound forms instantly. The early universe was the truckload. Dark matter halos were assembling in a sea of abundant matter. Gas was not scarce. It was everywhere. When slight overdensities emerged, they were surrounded by fuel on all sides. This is why the idea of too early becomes fragile. Too early compared to what? Compared to models calibrated on lower density epochs. Compared to simulations that may slightly underrepresent turbulent inflow. Compared to assumptions about how efficiently radiation pushes gas away, the universe does not owe us gradualism. It only obeys physics. And physics under extreme initial conditions can look explosive. Now let's descend into the heart of one of these galaxies Webb has detected. At its centre, gas is swirling inward along filamentary streams. The inflow rate may be dozens of solar masses per year. The gravitational potential well is deepening as dark matter accumulates. Stars ignite in dense clusters. Massive ones live fast, just a few million years, then explode. Their supernovae don't just disperse material randomly. They drive shock fronts that sweep up surrounding gas into dense shells. Those shells fragment. New stars form inside them. Meanwhile, mergers with nearby halos add more gas and stars, thickening the structure. Within a relatively short cosmic span, what began as a modest overdensity becomes a luminous, structured galaxy. Not perfect, not serene, but real, and bright enough to be seen from 13 billion light-years away. That brightness is critical, because to detect something at that distance, it must be extraordinarily luminous at its source. The inverse square law dims light rapidly with distance. Cosmic expansion stretches wavelengths and reduces energy further. So if Webb sees it clearly, the galaxy was blazing. There is no timid interpretation of that. And brightness at that level suggests either enormous stellar mass, intense starburst activity, or both. Which leads to another profound implication. If such galaxies are common, then the early universe may have had a higher star formation density than expected. In other words, more stars per unit volume per unit time. That shifts our picture of the cosmic timeline. The cosmic noon, the period about 10 billion years ago when star formation across the universe peaked, may not have been the only dramatic era. There may have been an earlier surge, compressed and intense. A primordial crescendo. Now widen the frame. Every galaxy we see from that epoch is embedded in the expanding fabric of space-time. The expansion rate itself depends on dark energy and matter density. The cosmic microwave background provides precise constraints on those parameters. If early galaxies are more abundant or massive than predicted, scientists will examine whether small adjustments in parameters such as the amplitude of initial density fluctuations could reconcile observations. This is how science breathes. Not by collapsing under anomaly, but by adjusting to it. But emotionally, something else is happening. The universe is becoming less predictable in its infancy. And that unpredictability is thrilling, because it suggests there are chapters of cosmic history that were more dynamic, more chaotic, more productive than we imagined. The early cosmos may have been the most extreme environment for structure formation it will ever experience. Today, dark energy accelerates expansion, galaxies drift apart, gas reservoirs are depleted, star formation slows. In trillions of years, the universe will be even quieter, fewer new stars, more aging remnants. But at the beginning, it was crowded, intense, competitive, regions of space racing to collapse first, Halus merging in rapid succession, black holes potentially forming through direct collapse mechanisms, massive gas clouds bypassing normal star formation and plunging straight into singularity. These are not gentle processes. They are decisive. And the fact that we are seeing mature galaxies at such early times suggests that some regions of the universe won early in that competition. They reached critical mass quickly. They ignited sooner. They grew faster. And because of cosmic expansion, their early advantage is frozen in the light we now observe. There is a kind of cosmic inequality in that idea. Some regions of the early universe surged ahead while others lagged. Density fluctuations, though tiny at the start, amplified into massive differences. This is the nature of gravity. It rewards the slightly denser. It magnifies advantage. And over time, those advantages compound into galaxies, into clusters, into superclusters spanning hundreds of millions of light years. When Webb detects a galaxy that should not exist, it is revealing one of those early winners, a region where conditions aligned perfectly for rapid growth. Now anchor that back to us. The Milky Way itself formed through mergers and accretion over billions of years. Our Sun formed 4.6 billion years ago, long after the peak of cosmic star formation. We are children of a middle-aged universe. But the light we are seeing now comes from its adolescence, from its most energetic growth spurt. And that perspective shifts something fundamental. We often think of progress as slow and steady, but the universe suggests something different. Under the right conditions, growth can be explosive. Structure can surge. Complexity can emerge faster than expected. The galaxy Webb has detected does not violate physics. It demonstrates how fiercely physics can operate when fuel is abundant and space is dense. And as more deep field surveys come in, as more redshifts are confirmed, as more masses are estimated, we may find that the early universe was not sparsely populated with tentative sparks. It may have been crowded with ambition. Ambition written in hydrogen and helium. Ambition driven by gravity. ambition blazing across billions of light years, until it reached us. Until it reached us and forced us to admit something profound. The universe did not tiptoe into complexity. It lunged. For decades, our mental image of cosmic evolution followed a kind of calm progression. First, the smooth afterglow of the Big Bang, then gradual clumping, then the first shy stars, then modest galaxies, slowly merging into larger ones. Orderly, measured, predictable. But the galaxies James Webb is revealing do not feel orderly. They feel impatient. And impatience at cosmic scale is a staggering concept. Because when we say early, we're not talking about thousands of years. We're talking about hundreds of millions of years after the birth of space and time. That sounds long to us. It is older than complex life on Earth. But cosmically, it is infancy. If the universe were a human lifespan of 80 years, these galaxies appear within the first few months of life. And yet they are already structured, already luminous, already chemically evolving. That should make you pause, because it means that the ingredients for complexity, gravity, gas, dark matter, radiation combine into organized systems almost immediately once conditions allow. And those conditions were brutal. The background radiation field was stronger, the density of matter was higher, collisions between halos were more frequent, the cosmic microwave background itself was warmer, bathing everything in a faint heat glow. This was not a quiet nursery. It was a crowded arena. And in arenas, growth can be competitive. Let's consider another possibility scientists are exploring. Perhaps some of these galaxies are not merely forming stars rapidly, but forming them differently. If the initial mass function, the distribution of star masses at birth, was skewed toward more massive stars in the early universe, that would change everything. Massive stars are brighter. Much brighter. A population dominated by heavy stars could produce enormous luminosity without requiring as much total stellar mass as we currently estimate. That means some of these galaxies might look heavier than they truly are because their stellar populations are unusually radiant. If that's the case, the early universe wasn't necessarily breaking our models. It was choosing a different stellar strategy. Brighter, hotter, shorter-lived. But even that explanation reinforces the same theme. The early cosmos was extreme. Either galaxies grew more mass faster than expected, or they formed stars with extraordinary intensity, or both. None of those paths are gentle. Now step inside one of these early galaxies again. The interstellar medium is thick. Gas clouds are denser than in present-day galaxies. Turbulence runs high. Radiation fields are intense. Supernovae are frequent. Black holes at the centre may be feeding at high rates, producing accretion disks that shine with ferocious energy. This is not a serene spiral like the Milky Way. It is a construction site under floodlights. And yet, within that chaos, structure stabilizes. Spiral arms may not be fully formed yet, but gravitational order is emerging. Stars orbit. Clusters settle into patterns. Dark matter halos hold everything together invisibly. This is the paradox of the universe. Violence produces architecture. Explosions produce chemistry. Collapse produces light. When Webb captures these galaxies, it is not just showing us brightness. It is showing us resilience. Because against expansion, against radiation pressure, against explosive feedback, gravity held enough matter together long enough to build something coherent. That is an achievement at cosmic scale. And the more we think about it, the more we realize how close this all sits to the edge of possibility. If expansion had been slightly faster, matter might have diluted too quickly for such early growth. If initial density fluctuations had been slightly weaker, collapse might have taken longer. If dark matter behaved differently, halos might not have formed in time. The universe walks a narrow path. And in its earliest era, it seems to have walked it boldly. Now imagine watching this from Earth. You stand under a night sky, unaware that every point of light you see is a survivor of billions of years of cosmic evolution, unaware that the earliest galaxies blazed long before our planet formed. You breathe air forged in stars that lived and died in earlier galaxies, descendants of those first bursts of light. The oxygen in your lungs was not created in a quiet era. It was born in violence, and that violence may have begun sooner than we thought. There is something almost intimate about that, because when we talk about galaxies forming too early, we are really talking about the acceleration of our own origin story. If heavy elements formed earlier, then the raw materials for planets circulated earlier. If planets formed earlier, then the possibility of complex chemistry arose earlier. We are not claiming ancient civilizations in the deep past of the universe, but we are acknowledging that the cosmic timeline toward habitability may have started running sooner. That realization stretches our sense of cosmic history. It makes the universe feel older in its maturity, even when it was young in age. And it forces us to reconsider the phrase should not exist. The galaxy Webb detected does exist. It shines in ancient infrared light. It obeys gravity. It follows thermodynamics. It fits within physics. What it challenges is expectation. And expectations are human. The universe does not grow according to our comfort. It grows according to density, gravity, and energy. In its earliest chapters, those forces were amplified. Everything was closer together. Everything was hotter. Everything was primed. Under those conditions, hesitation is rare. What we are witnessing is not a violation. It is acceleration. An early surge of cosmic construction that may have set the stage for everything that followed. And as Webb continues to look deeper, longer exposures, fainter targets, sharper spectra, we may find that this early boldness is not the exception. It may be the rule. If so, the universe did not gradually wake from darkness. It burst into architecture. It rushed toward complexity. And we, billions of years later, are only now seeing how quickly it began. And the deeper that realization sinks in, the more radical it becomes. Because if the universe rushed toward complexity, then the first chapter of cosmic history was not a blank page slowly filled in. It was densely written from the start. Let's widen the frame one more time. When we look at the most distant galaxies, we are seeing light that left them when space itself was still compact. The observable universe was smaller not because it had edges, but because distances between everything were compressed. Imagine taking every galaxy within 1 billion light-years today and squeezing them into a region a fraction of that size. Interactions would skyrocket. Mergers would be common. Gravitational tides would constantly reshape structure. That was the early cosmos. It was a place where isolation was rare. And isolation is what slows growth. In today's universe, galaxies can drift alone for billions of years, forming stars gradually from limited gas supplies. But early on, galaxies were fed by continuous streams from the cosmic web, filaments of dark matter channeled hydrogen like arteries feeding a heart. If a galaxy sat at a node where multiple filaments intersected, it would be inundated with fuel. That could explain the rapid mass assembly Webb is detecting. These galaxies might not be anomalies in empty space. They might be positioned at cosmic intersections, highways of matter converging in dense regions. In that case, what we are seeing is not random luck. It is geometry. The architecture of the cosmic web determining which region surged ahead. Now imagine the view from inside one of those regions. The night sky would not be sparse. Neighbouring proto-galaxies would glow nearby, separated by distances far smaller than those between large galaxies today. Collisions would distort shapes. Tidal streams of stars would arc between merging systems. The early universe was not peaceful. It was interactive. And interaction accelerates evolution. When galaxies merge, gas clouds collide and compress. Star formation rates spike. Central black holes are fed. Structure reorganizes. Each merger is like adding oxygen to a fire. If mergers happened frequently in certain dense regions, growth would not be linear. It would be punctuated. Sudden jumps in mass, sudden increases in brightness, sudden chemical enrichment. This fits the pattern Webb is uncovering. And here's where it becomes even more profound. The cosmic microwave background, the oldest light we can see, contains tiny fluctuations that encode the seeds of all later structure. Those fluctuations are incredibly precise, measured to extraordinary accuracy. They tell us how much initial lumpiness the universe had. If early galaxies are more massive or more numerous than expected, scientists may examine whether those initial fluctuations allowed slightly more small-scale power than previously modelled. Even a subtle adjustment in those early density variations could amplify dramatically over hundreds of millions of years. Small beginnings, large consequences. That is gravity's signature. But regardless of the technical refinements that follow, the emotional truth remains. The early universe was not fragile. It was fertile. Fertility at cosmic scale is staggering. Because fertility means the capacity to produce, to generate structure, to repeat cycles of birth and death rapidly. And birth and death are exactly what the first generations of stars embodied. Those first stars likely lived fast and died young. Their supernovae seeded space with heavier elements. Those elements allowed gas to cool more efficiently. Cooling allowed smaller stars to form. Smaller stars live longer. This cascading transformation may have unfolded quickly inside dense early galaxies, which means that by the time the universe was only a few 100 million years old, it was already chemically evolving, already differentiating, already diversifying. That word matters, diversifying. A purely hydrogen-helium universe is simple. A universe with carbon, oxygen, nitrogen, silicon, iron, that is a universe capable of complexity. And complexity may have begun spreading earlier than we thought. Now pause and feel the scale of that statement. When the galaxy Webb detected emitted the photons we now capture, Earth did not exist. The Sun did not exist. Our galaxy was still assembling itself through mergers. And yet, somewhere in that early galaxy, heavy elements were being forged. Somewhere, supernovae were exploding. Somewhere, black holes may have been growing. Those processes were not waiting for us. They were already underway. We are late observers of an early blaze, and that perspective changes how we understand ourselves. We are not the culmination of a slow cosmic patience. We are the distant consequence of an early surge, an early decision by gravity to collapse matter into stars, an early cascade of fusion reactions creating the periodic table, an early web of galaxies shaping the large-scale universe. The galaxy that should not exist is a messenger from that surge. It tells us that the universe may have moved faster than we expected. That structure may have matured earlier, that the dark ages may have ended abruptly. And there is something deeply humbling about that, because it reminds us that the cosmos does not unfold according to our intuitions about pacing. We expect beginnings to be tentative, but the universe began at unimaginable density and temperature. Its starting conditions were extreme. Why wouldn't its early growth be extreme too? James Webb is giving us a front-row seat to that extremity. Its mirrors gather photons that began their journey when the universe was less than 5% of its current age. Its instruments decode those photons into spectra fingerprints of elements, distances, star formation rates. From those faint signals, we reconstruct entire galaxies. Cities of stars, billions of suns burning in ancient space. And the message emerging is not subtle. The universe did not waste time becoming grand. It built quickly. It built violently. It built early. And as we continue to push our gaze closer to the Big Bang probing earlier epochs, fainter systems, higher redshifts, we may find that this early boldness is not rare. It may be woven into the very fabric of cosmic history. The first light was not a flicker. It was a surge. and we're only now beginning to see how powerful that surge truly was. And once you see that surge, you cannot unsee it. Because the idea of a galaxy too early is not just about distance. It is about rewriting the tempo of creation. For years, cosmology has been like reading a biography where the first chapters were sparse. We had the cosmic microwave background, a baby picture of the universe at 380,000 years old. Then we had mature galaxies billions of years later. The space in between was mostly inference. Webb has stepped into that gap. And what it is finding is not empty. It is crowded. Crowded with systems that appear far more evolved than a cautious timeline would predict. That crowding forces us to confront something uncomfortable. Perhaps our mental image of the early universe was too gentle. Because gentle beginnings make intuitive sense to us. Human development is gradual. Civilizations rise over centuries. Forests grow over decades. Mountains erode over millennia. But gravity does not think in decades. Gravity responds instantly to imbalance. The early universe was imbalance everywhere, tiny fluctuations amplified in a sea of dense matter. Once collapse began in certain regions, it could cascade. And here is the critical shift. We may have underestimated how nonlinear that cascade could be. Nonlinearity is where small differences explode into large outcomes. A region just slightly denser than its surroundings pulls in slightly more matter. That extra matter deepens the gravitational well. A deeper well attracts even more matter. The effect compounds. If inflow exceeds feedback, growth accelerates. If mergers occur during peak inflow, mass jumps. If black holes form and accrete efficiently, energy release reshapes the host galaxy. None of these steps are forbidden by physics. They are allowed, and in a dense early cosmos they may have been common. Now let's return to the observational side. When Webb detects one of these ancient galaxies, astronomers estimate its redshift, the degree to which its light has been stretched by expansion. Higher redshift means earlier time. Some of these galaxies appear at redshifts corresponding to just 300 to 400 million years after the Big Bang. At that time, the universe was still undergoing reionization. Neutral hydrogen was being ionized by ultraviolet light from the first luminous sources. Detecting bright galaxies in this epoch means those sources were already active and powerful. They were not tentative sparks. They were floodlights. And floodlights clear fog quickly. This ties directly to one of the biggest questions in cosmology: what reionized the universe? Was it numerous small galaxies, collectively ionizing space? Was it rarer but extremely bright systems? Was it early quasars powered by rapidly growing black holes? If Webb is revealing surprisingly luminous galaxies at very early times, then they may have played a larger role than previously assumed. That elevates them from curiosities to architects. Architects of transparency. Architects of the modern universe. Now shift perspective again. Imagine compressing the first billion years of the universe into a single hour. For the first few minutes, nothing shines. Then, suddenly, lights begin flickering on across a dark landscape. Within what feels like moments, entire clusters of lights blaze into existence. Structures form, merge, brighten. Before the hour ends, the landscape is already complex. That is what Webb is suggesting. The early universe may have passed through its most explosive growth phase astonishingly quickly. And that rapid growth has implications beyond galaxies. Because galaxies are ecosystems. They host stars. Stars host planetary systems. Planetary systems host chemistry. Chemistry, under the right conditions, can become biology. If galaxies matured earlier, if heavy elements circulated earlier, then the prerequisites for planets emerged earlier. We do not know how quickly planets began forming in the first billion years. But we know that once heavy elements exist, planet formation becomes possible. And Webb's galaxies imply those elements may have been present sooner than we expected. This stretches the cosmic horizon of possibility. It does not claim ancient civilizations hidden in the deep past, but it suggests that the universe may have been capable of complexity long before Earth was even a thought. That is humbling, because it reframes our timeline. We are not early. We are not central. We are latecomers to an ancient experiment in structure. The galaxy that should not exist is not an error in the script. It is a reminder that the script was always more intense than we imagined. And here is the final layer of tension. If these galaxies are confirmed as massive as they appear, cosmologists will adjust models, simulations will incorporate more aggressive star formation efficiencies, feedback prescriptions will be recalibrated, small-scale dark matter clustering may be re-examined. The framework will evolve. It always does. But the emotional impact remains. The universe did not wait around to become interesting. It became interesting almost immediately. And that revelation ripples forward. Because when we look at the night sky tonight, we are not just seeing distant stars. We are seeing survivors of a hyperactive youth. Galaxies that endured mergers, black hole growth, supernova storms. Galaxies whose ancestors ignited far earlier than we once believed. We are looking at the descendants of a cosmic growth spurt. James Webb is not breaking cosmology. It is accelerating our understanding of it. It is revealing that the first act of the universe may have been its most dramatic. And if that is true, then the phrase too early dissolves. There was no waiting period. No extended hesitation. Once gravity had matter to work with, it built. Fast, brilliantly, relentlessly, and the light from that relentless beginning is only now finishing its 13 billion year journey. Just in time for us to realize how quickly everything began. Just in time for us to realize that the universe's first act may have been its boldest. Because once you accept that galaxies were assembling at breathtaking speed only a few 100 million years after the Big Bang, another question rises immediately. What else ignited early? Galaxies are not isolated phenomena. They are frameworks. Within them, other extremes unfold. And at the heart of many galaxies sits one of the most extreme objects physics allows a black hole. Today, almost every massive galaxy we observe appears to host a supermassive black hole at its centre. The one in the Milky Way weighs about 4 million suns. Others weigh billions. Growing something that massive takes time, or at least that was the assumption. Black holes increase their mass by accreting matter, but there's a limit to how quickly they can do so without their own radiation pushing material away. This theoretical cap, the Eddington limit, suggests that steady growth should be constrained. Yet astronomers have found quasars actively feeding supermassive black holes less than 1 billion years after the Big Bang, already weighing 1 billion solar masses. That alone strained timelines. Now combine that with Webb's discovery of unexpectedly mature galaxies at even earlier times. Dense galaxies mean dense central regions. Dense central regions mean abundant fuel. Abundant fuel means black holes could grow faster. If early galaxies were building stars aggressively, they may also have been building black holes aggressively. And black holes are not passive. When actively accreting, they release extraordinary amounts of energy. Matter spiraling into the event horizon forms an accretion disk heated to millions of degrees. Magnetic fields twist. Jets of relativistic particles blast outward at near-light speed. A quasar can outshine its host galaxy. In the early universe, such objects would not just illuminate space. They would reshape it. Radiation from quasars could ionize vast regions of hydrogen. Jets could stir and heat surrounding gas, influencing star formation rates. Entire galactic ecosystems could pivot around these central engines. So now the early universe begins to look less like scattered sparks and more like a network of power stations. Galaxies forming quickly. Black holes igniting early. Reionization accelerating. Heavy elements dispersing. This is no longer a gentle dawn. It is an electrical storm. And the deeper implication is this. The early universe may have reached structural maturity astonishingly fast. Not perfection, not stability, but functional complexity. Enough stars to reshape gas, enough black holes to influence galaxies, enough enrichment to alter chemistry, all within a cosmic blink. Let's ground this again. The galaxy Webb detected emitted its light when the universe was perhaps 300 million years old. That is about 2% of its current age. 2%. Imagine a human reaching adulthood at 2 years old. That is the scale of acceleration we are contemplating. And yet, nothing about this violates known laws. Gravity does not have a minimum waiting period. Fusion does not require patience beyond pressure and temperature thresholds. Dark matter hollows form as soon as density fluctuations cross critical limits. The early universe met those limits quickly. So perhaps the phrase should not exist reflects our expectations more than reality. The universe had everything it needed from the beginning. Mass, energy, fluctuations, time. Time, in particular, is deceptive. 300 million years sounds brief compared to 13.8 billion. But 300 million years is long enough for countless generations of massive stars to live and die. A massive star may burn out in just a few million years. In 300 million years, that's dozens of stellar generations. Plenty of opportunity for enrichment. Plenty of opportunity for collapse and recollapse. Plenty of opportunity for growth. We may have underestimated how much can happen in what feels like a short cosmic window. Because our intuition for time is anchored to human lifespans. The universe operates on different rhythms. And under high-density conditions, those rhythms accelerate. Now zoom out once more. The observable universe contains perhaps 2 trillion galaxies, each one the product of early density fluctuations amplified over billions of years. If even a fraction of them began forming robustly within the first few 100 million years, then the early cosmos was not sparsely lit. It was vibrant. Pockets of intense activity scattered across expanding space. And as expansion stretched distances and cooled temperatures, growth gradually slowed. Star formation peaked billions of years later, then declined. But the seeds of that later abundance may have been planted extraordinarily early. Which brings us back to something subtle but powerful. When we say early galaxy, we are really talking about ancestry. The Milky Way did not appear from nowhere. It grew from smaller progenitors, ancient systems that merged and evolved over time. Some of those progenitors may have looked like the galaxies Webb is now detecting. We are looking at distant cousins of our own galactic lineage, ancestors in the cosmic family tree. Their stars lived and died, enriching gas that would later become part of larger structures. Eventually, through countless mergers and accretions, material from systems like these contributed to galaxies like ours. In that sense, this discovery is not remote. It is personal, because the atoms in your body were forged in stars whose lineage traces back to those early bursts of formation. The galaxy that should not exist may represent one of the earliest chapters in the story that eventually produced you. That realization collapses distance. 13 billion light-years no longer feels abstract. It feels ancestral. And that is perhaps the most profound shift of all. James Webb is not just finding anomalies. It is revealing how quickly the universe began telling its story. A story of collapse and ignition, of enrichment and structure, of light breaking through darkness earlier than we imagined. The early cosmos was not hesitant. It was ambitious. It built frameworks for everything that followed. And we, standing on a small planet orbiting a middle-aged star, are only now understanding how fast that ambition ignited. The beginning was not quiet. It was a surge. And that surge echoes through every galaxy we see today, including our own. Because when we look at the Milky Way, we're not looking at a single uninterrupted structure. We are looking at layers of history, stellar populations of different ages, Streams of stars torn from smaller galaxies, ancient globular clusters that may predate the bulk of the disk. Our galaxy is a mosaic, and mosaics are built from fragments. Some of those fragments were born in the early universe, perhaps in systems not unlike the galaxies Webb is now revealing. Small, intense, fast-growing structures that collided, merged, and were absorbed into larger frameworks over billions of years. That means when we stare at a galaxy 13 billion light-years away, we may be glimpsing the kind of building block that ultimately shaped our own home. This is not distant trivia. This is deep ancestry. But ancestry implies a process, and the process we are uncovering appears far more accelerated than we once imagined. Let's slow down not the intensity but the pacing. Imagine the early universe again, dense and dark. The first stars ignite, massive, blue, unstable. They flood their surroundings with radiation, they explode, their shock waves compress nearby gas. New stars ignite in clusters. Within tens of millions of years, heavy elements begin to circulate locally. Within hundreds of millions of years, entire galaxies emerge as coherent structures. Now extend that forward. Galaxies merge. Dark matter halos combine. Gas funnels inward. Black holes grow. Star formation surges, then regulates, then surges again. All of this happens before Earth exists. Before the sun ignites. Before our solar system's dust disk even forms. By the time our planet appears, the universe has already undergone billions of years of structural evolution. It has already survived its most crowded epoch. Already experienced its most intense star-forming periods. Already built the scaffolding of the cosmic web stretching hundreds of millions of light-years. The early galaxy web detected is a fossil from that epoch. But it is not dead. Its light is alive. It travelled for 13 billion years to reach us, crossing expanding space that stretched its wavelengths into infrared. Each photon is a messenger, and those messengers are telling us something profound. The universe did not struggle to organise itself. It leapt. Now consider the emotional shift this creates. For much of human history, the night sky felt timeless and unchanging. Stars seemed eternal. The cosmos seemed static. Then we learned that stars are born and die. Then we learned that galaxies evolve. Then we learned that the universe itself expands. Now we are learning that its earlier structures may have emerged faster than we thought. Every layer of understanding reveals a cosmos that is more dynamic, more urgent, more alive than previous generations imagined. And there is something deeply human about that realization. Because we are creatures who equate beginnings with vulnerability. Infancy is fragile. New systems are unstable. Growth is slow. But the universe's infancy may have been anything but fragile. It was powered by density, fueled by gravity, and ignited by fusion. It was capable of producing brilliance almost immediately. This does not mean it was stable. Far from it. The early cosmos was violent. Starbursts, supernovae, black hole accretion, mergers all happening in compressed space. But violence does not preclude productivity. In fact, in astrophysics, it often enables it. Supernovae distribute elements. Mergers trigger star formation. Accretion fuels radiation that reshapes environments. The early universe was not peaceful. It was transformative. And transformation is what allows complexity to arise. Now imagine a timeline stretching forward from that early galaxy web detected. Its stars age. Some collapse into neutron stars or black holes. It merges with neighbours. Its gas supply fluctuates. Over billions of years. It may grow into something unrecognisable from its early form. Or it may be torn apart and absorbed by a larger galaxy. Either way, its matter continues. Its heavy elements mix into broader structures. Eventually, through chains of mergers and star formation cycles, atoms forged in early systems become part of planets, atmospheres, oceans. The oxygen you breathe may trace its origin back through generations of stars to an epoch when the universe was only a few 100 million years old. The calcium in your bones, the iron in your blood products of supernovae that may have occurred long before the Milky Way reached its current form. So when we say a galaxy should not exist, we're talking about the acceleration of our own origin story. If galaxies matured earlier, then the cosmic supply chain of heavy elements began earlier. And that pushes back the moment when the universe became capable of complexity. This is not speculation about aliens in the deep past. It is recognition that the universe's chemical maturity may have arrived sooner than we expected. And that recognition alters perspective. We often see ourselves as late products of a long, patient build-up, but perhaps we are the distant echo of an early surge. An early furnace burning brighter and faster than anticipated. James Webb was built to look back to first light. Its golden mirror unfolds like a mechanical flower in deep space. Its sun shield blocks the warmth of the sun, keeping its instruments cold enough to detect faint infrared whispers. And those whispers are telling a story of acceleration, of galaxies assembling quickly, of stars igniting in waves, of structure emerging almost immediately after darkness lifted. The early universe was not empty for long. It did not drift slowly toward grandeur. It rushed. And as we continue to analyze spectra, confirm redshifts, refine mass estimates, and expand surveys, that rush may become clearer. The cosmos may have front-loaded its drama. Its most intense growth phase may have occurred at the very beginning. And that changes the emotional arc of everything, because it means the universe did not gradually become capable of wonder. It was capable of wonder almost from the start. And we, billions of years later, are only now catching the light from that audacious beginning. Realizing how quickly the story truly began forces us to confront something even larger than a single galaxy. It forces us to reconsider the tempo of the entire cosmos. Because when we peel back 13 billion years and find fully formed galaxies staring back at us, we're not just adjusting a chart on a whiteboard. We're adjusting our intuition about how reality behaves under extreme conditions. We assumed the early universe would hesitate. Instead, it accelerated. And acceleration has consequences. If galaxies assembled rapidly, then large-scale structure may have crystallized earlier than expected. The cosmic web, those titanic filaments of dark matter, connecting clusters across hundreds of millions of light-years, may have become dynamically active sooner. Imagine the universe not as a slow-growing forest, but as a lightning strike branching across the sky. Each branch represents matter collapsing, igniting, merging. The first few 100 million years were not empty stretches of time. They were ignition windows. Now let's confront the most destabilizing implication. If multiple galaxies this massive exist at such early epochs, then our simulations, no matter how powerful, may have underestimated how violently nonlinear early structure formation was. And nonlinear systems are notorious for surprises. In a linear system, change is proportional, double the input, double the output. In a nonlinear system, small differences explode. Gravity is nonlinear. Add a little more mass to a region, and its pull increases. That increased pull attracts more mass, which increases pull further. Compound growth. Runaway collapse. The early universe was primed for runaway behavior. High density. Abundant fuel. Minimal separation. Under those conditions, too early may simply mean we underestimated compounding. And compounding is one of the most powerful forces in nature. Now feel the scale again. When Webb sees a galaxy at redshift 10 or higher, we're observing light emitted when the universe was perhaps 400 million years old. That light has travelled across expanding space for 13.4 billion years. During that time, galaxies collided. Stars were born and died trillions of times. Black holes merged, releasing gravitational waves that rippled through space-time. Planets formed. On at least one of them, chemistry became consciousness. And yet that ancient light kept travelling, uninterrupted, unaffected, until it struck a mirror engineered by a species that did not exist when it left. There is something staggering about that symmetry. The early universe building galaxies at astonishing speed. The late universe building telescopes capable of seeing them. Two surges of complexity separated by billions of years. One driven by gravity, the other driven by curiosity. And curiosity is not separate from gravity's story. It is its consequence. Because the heavy elements that make up human brains were forged in stars whose lineage traces back to early galaxies. If those galaxies formed earlier, then the chain reaction that eventually produced observers began earlier. Again, this is not about ancient civilizations. It is about chemical inevitability. Once stars ignite, once supernovae scatter elements, once planets form, complexity has a pathway. And the earlier that pathway opens, the more profound the timeline becomes. Now consider another subtle implication. The early universe was hotter not just in stars, but in background radiation. The cosmic microwave background at 300 million years old was significantly warmer than today. That background heat influences how gas cools, how structures collapse, how molecules form. And yet, despite that warmer environment, galaxies still assembled rapidly, which suggests that the cooling mechanisms inside dense halos were powerful enough to overcome environmental heat. It suggests resilience. Even when bathed in residual Big Bang radiation, gravity found a way to organize matter. And that resilience is worth lingering on, because the universe did not start with favorable conditions for delicate chemistry. It started with extreme temperature, extreme expansion, extreme density contrasts. And within a fraction of its current age, it was already producing structured galaxies. That reframes our concept of fragility. The early cosmos was not a delicate embryo. It was a pressure chamber. And pressure chambers accelerate reactions. Now zoom forward one final time. Today, the universe is expanding faster due to dark energy. Galaxies drift apart. In the distant future, distant galaxies will slip beyond our observable horizon, carried away by expansion. Star formation rates are declining, gas supplies are dwindling, the cosmos is aging. We live in a relatively calm era. But Webb's discoveries remind us that the calm came after the storm, after the initial surge, after gravity's most crowded epoch. The galaxy that should not exist is not an exception to cosmic order. It is evidence that the early universe may have been more extreme than our comfortable narratives allowed. It is a signal from the era when everything was closer, hotter, denser, more volatile. And that volatility built the foundations of everything we know. When we look at that ancient galaxy, we are not seeing a mistake. We are seeing gravity at full throttle. We are seeing fusion in overdrive. We are seeing dark matter sculpting structure with ruthless efficiency. And we are seeing how quickly the universe learned to build. That realization does not destabilize science. It energizes it. Because every time the universe exceeds our expectations, it invites us to refine them. To look deeper, to measure more precisely, to simulate more aggressively. James Webb is still in its early years of operation. It will gather deeper fields, longer exposures, sharper spectra. It will likely find even earlier candidates, even fainter whispers from closer to the Big Bang. And each one will add detail to this accelerating narrative. The beginning was not slow. It was explosive. It was nonlinear. It was ambitious. And as we stand here on a planet forged from ancient stellar debris, orbiting a star born long after that first surge, we are finally seeing how quickly the universe began telling its story. Not with hesitation, but with fire. Not with hesitation, but with fire. And fire spreads. Once the first galaxies ignited, they did not exist in isolation. Their radiation spilled outward, Their supernovae reshaped nearby gas. Their gravity tugged at neighbours. The early universe was not a gallery of disconnected lights. It was a chain reaction unfolding across the cosmic web. Picture a dark landscape where sparks begin igniting in scattered clusters. Each spark grows into a blaze. Each blaze throws off embers. Those embers land elsewhere, igniting new fires. That is what early structure formation may have resembled. A cascade. And cascades are fast. The discovery of a galaxy that should not exist at such an early epoch is not merely about one object being too massive. It is about recognizing that once ignition began, growth could accelerate across entire regions. Because galaxies are not just collections of stars. They are gravitational engines. Once enough mass accumulates in one place, its pull intensifies, gas flows more efficiently along filaments, mergers become more dramatic, central black holes feed more aggressively. Momentum builds. And in the early universe, the momentum had little resistance. Today, dark energy stretches space faster and faster. Galaxies recede from one another. Growth slows on the larger scales. But 13 billion years ago, dark energy was negligible compared to matter. Gravity dominated. Expansion was decelerating under the weight of matter's pull. The cosmic tug-of-war favoured collapse. That matters. Because when gravity is stronger relative to expansion, structures can assemble faster. This is not speculation. It is encoded in the equations of general relativity. In the matter-dominated era of the universe, density fluctuations grow more efficiently. The early universe was matter-dominated, which means it was primed for structure. And when you combine that with high overall density, you create ideal conditions for rapid assembly. So perhaps the real surprise is not that galaxies formed quickly. Perhaps the surprise is that we ever expected them to form slowly. But there is still tension. Even under matter domination, simulations predicted a certain pace, and Webb's galaxies seem to sit at the upper edge or beyond of those expectations. Which means either the early universe exploited every available efficiency, or there are subtleties in star formation physics, feedback processes, or dark matter clustering that we are still refining. That is not a crisis. It is a frontier. And frontiers are where science becomes alive. Now let's return to the human frame. When you look at a deep field image from Webb, it appears almost abstract, thousands of faint reddish smudges scattered across blackness. But each smudge is a galaxy. Each galaxy contains billions of stars. Each star may host planets. And some of those smudges are so distant that their light left when the universe was barely beginning. You are looking at infancy. But it does not look like infancy. It looks mature, structured, layered, alive with complexity. And that visual contradiction is powerful, because it breaks our narrative instinct. We want beginnings to look simple. But the universe does not care about our storytelling preferences. Under the right physical conditions, complexity can bloom almost immediately. And that realization has a psychological weight. It makes the cosmos feel less linear, less gradual, more explosive. We often imagine that we are the result of a slow, almost inevitable build-up of structure across billions of years. But if the early universe surged so dramatically, then the foundations of our existence were laid in a burst. The heavy elements in your body trace back to stars that may descend from galaxies that formed astonishingly early. The iron in your blood was born in a supernova. That supernova's progenitor star was born in a galaxy. The galaxy's ancestors may have resembled the systems Webb is now detecting. The timeline from Big Bang to biology may be more compressed at the front end than we imagined. And that compression changes perspective. Because it suggests that the universe's capacity for complexity was not something that emerged slowly over most of its lifetime. It was present from near the beginning. All it required was gravity, density, and time measured in millions, not billions of years. Now zoom outward one last time. The observable universe spans about 93 billion light-years in diameter today. It contains perhaps trillions of galaxies. Every one of them traces its origin back to tiny fluctuations in the early universe. Those fluctuations were imprinted in the cosmic microwave background. From those almost imperceptible differences, everything grew. Webb's discovery suggests that the growth curve in the earliest epochs may have been steeper than expected. A sharper rise, a faster climb. And if that is true, then the first chapter of cosmic history was not a prologue. It was a crescendo, a universe that wasted no time becoming grand. As we continue to peer deeper toward redshifts even higher, toward times even closer to the Big Bang, we may approach the true dawn of galaxy formation. Perhaps we will find even earlier systems. Perhaps we will see the transition from pure darkness to the first sparks. And perhaps we'll realize that the gap between nothing shining and galaxies blazing was astonishingly narrow, that the universe crossed that threshold quickly, and that we have only just begun to grasp how rapid that crossing was. Because in the end, the phrase "should not exist" reveals more about us than about the cosmos. It reveals our expectation of patience, our assumption of gradualism, our comfort with slow evolution. But the universe began in an explosion. It expanded at extraordinary rates. It cooled, clumped, ignited. And it may have done so with breathtaking speed. James Webb did not break the universe. It broke our sense of pacing. It showed us that the cosmos may have front-loaded its brilliance, that the first few 100 million years were not quiet rehearsals. But opening night was not the end of the performance. It was the moment the curtain rose and the universe stepped forward already aflame. When James Webb detected a galaxy that should not exist so early in time, it did not uncover a glitch in reality. It revealed that reality, under extreme conditions, moves faster than our instincts allow. We expected infancy. We found architecture. We expected scattered sparks. We found cities of stars. And the deeper we follow that revelation, the more it reshapes our sense of cosmic narrative. Because the early universe was not just forming galaxies, it was establishing the framework for everything that would follow. Dark matter sculpted invisible scaffolding across space. Gas streamed along those filaments. Stars ignited in waves. Supernovae forged heavy elements. Black holes anchored galactic centers. Radiation cleared the cosmic fog. All within a fraction of the universe's current age. This was not a rehearsal. It was a surge of structure under the most intense physical conditions the cosmos would ever experience. High density, abundant fuel, minimal dilution, gravity at maximum leverage. And from that leverage came acceleration. The galaxy Webb saw massive, luminous, unexpectedly mature exists because gravity compounded relentlessly from the smallest imbalances imprinted at the beginning. 1 part in 100,000. That was enough. Enough to seed the cosmic web. Enough to create halos. Enough to funnel gas into dense regions. Enough to ignite the first stars and trigger cascading growth. The universe did not need billions of years to begin organizing itself. It needed conditions. And those conditions were present almost immediately. When we say too early, we are really saying earlier than our imagination was prepared for. But physics was prepared. Gravity was prepared. Fusion was prepared. Dark matter was already shaping the stage. Time, even in hundreds of millions of years, was sufficient for dozens of stellar generations. And once the first stars lived and died, chemical complexity accelerated. Carbon, oxygen, nitrogen, iron, the ingredients for planets, atmospheres, oceans. The elements in your body were set on their path in that early blaze, which means this discovery is not distant trivia. It is ancestral revelation. The light Webb captures left its galaxy before Earth existed. It crossed expanding space for 13 billion years. It arrived here in an era when the universe is calmer, quieter, older. It reached a species capable of building a telescope cold enough, sensitive enough, precise enough to read its ancient signature. That is the symmetry. The early universe surged into structure. The late universe surged into awareness. We are the echo of that first acceleration. And perhaps the most profound realization is this. The universe did not gradually become capable of wonder. It was capable of wonder almost immediately. Within a few 100 million years of the Big Bang, it was already assembling galaxies complex enough to challenge our expectations, already forging the heavy elements that would later build worlds, already shaping the cosmic web that still guides the motion of galaxies today. The beginning was not timid. It was bold. It was nonlinear. It was ambitious. And that ambition still reverberates. When you look at the night sky now, you are not looking at a slow, sleepy cosmos. You are looking at the descendants of an ancient growth spurt. Galaxies that survived mergers, radiation storms, black hole eruptions. Stars that formed from gas enriched by ancestors that burned billions of years before our sun ignited. The Milky Way itself is a veteran of that early intensity. Its oldest stars are relics of an era when structure was assembling rapidly across dense space. We live inside the aftermath of that surge. And James Webb has given us something extraordinary. Perspective. Perspective that compresses the early universe into something dynamic, crowded, urgent. Perspective that reveals how quickly gravity can turn simplicity into architecture. Perspective that replaces should not exist with a deeper understanding. Of course it exists. Under those conditions, why wouldn't it? The cosmos began in explosion and expansion. It carried within it tiny fluctuations, imperfections that became galaxies. It cooled just enough for atoms to form. It clumped just enough for stars to ignite. It accelerated just enough for structure to mature early. And from that early maturity came everything else. We often think of ourselves as the product of a long cosmic patience, but perhaps we are the product of a short cosmic fury, an early blaze of structure that set the stage for all subsequent evolution. The galaxy Webb detected is not an anomaly at the edge of time. It is a reminder that the universe's opening act may have been its most dramatic. That complexity did not creep into existence. It erupted. And now, billions of years later, we stand at the far end of that eruption. Small, aware, included. Finally seeing how quickly the cosmos learned to build,